Hey everyone, and welcome to this explainer. Today we're diving into a critical yet almost entirely invisible crisis that is literally threatening our global food supply. And yeah, that means the food right there on your plate and the cotton hanging in your closet. We hear a ton about climate and carbon, but right beneath our feet, there are two silent emergencies unfolding at the exact same time: rapid water depletion and soil degradation. It's a massive story about how we actually feed ourselves and the completely hidden costs we're racking up just to make it happen.
Okay, let's dive right into this roadmap. We've got 5 key areas today: the liquid we can't replace, 4 ways we irrigate, mining our hidden aquifers, the salt in our soil, and finally, the absolute tragedy of the Aral Sea. Starting off with Section 1, the liquid we can't replace. Now, when you or I think about water use, we probably picture leaving the sprinklers on too long, or maybe massive industrial factories, right? Well, it turns out agriculture actually completely dominates the picture, taking up a staggering 70% slice of all global freshwater withdrawals. Just think about that. That is more than industry and city use put together. And the water that keeps these crops alive, it's not just cleanly consumed. Much of it evaporates into thin air before it even reaches the roots, or it just runs right off the field. Because our aquifers are shrinking and rivers are maxed out, figuring out how to handle this 70% slice is quite literally one of the only paths we have left to feed a growing population without running completely dry.
And here is the really harsh reality we can't just engineer our way out of. Water has absolutely no synthetic equivalent. If a farmer runs out of a specific fertilizer or pesticide, well, you can usually find an alternative chemical to keep the yields up. But photosynthesis, plant metabolism, they demand liquid water, full stop. We simply can't breed a plant that doesn't need to drink. And that non-substitutability makes this constraint totally different from almost any other resource challenge we face on Earth.
Which brings us to Section 2, 4 ways we irrigate.
Now, what's really interesting about this slide is the dramatic difference in efficiency across the board. Down on the low end, you've got flood irrigation, which is literally just releasing gravity-driven water to wash across a field. It sits at a surprisingly low 50% efficiency. That means half the water is just lost. It's cheap to set up, so it's super common in developing countries. Then, moving up, we have sprinkler systems hitting around 75%. Oh, and I should briefly mention furrow irrigation, where water flows down channels between crop rows, sits right in the middle at about 60%. But then look at drip irrigation. It sits incredibly high at 90%.
So what exactly is drip irrigation? Basically, it's a micro-irrigation method that delivers water directly to the plant's root zone, using low-pressure emitters sitting right on or just under the soil. By not spraying water up into the air or flooding an entire field, you drastically cut down on evaporation and lower the risk of ruining the soil. Sure, it's the most expensive setup out of the 4, but pioneers in water-scarce areas like Israel back in the 60s and heavily farmed areas like California's Central Valley today, they rely on it heavily. It's not just a farming choice, it's an absolute investment in survival.
All right, moving right along to Section 3, mining our hidden aquifers.
To really wrap our heads around this, we need to talk about fossil water. We're talking about massive subsurface aquifers that filled up thousands, sometimes tens of thousands of years ago during ancient, much wetter climates. And today, their recharge rate is effectively zero on a human timescale. Think of it exactly like a giant subterranean savings account. Mining this fossil water for irrigation is what's keeping our massive agricultural productivity going today, for sure. But we're totally foreclosing on the future. We're burning through our life savings with zero income to replace it. To show you just how wildly unsustainable this is, get a load of this extraction to recharge ratio, 60-1. In parts of the massive Ogallala Aquifer, which basically props up the U.S. Great Plains and supports 30% of all groundwater irrigated cropland in the country, the natural recharge is only about half a centimeter a year. The withdrawals? Over 30 centimeters a year in some places, 60-1. And the crazy part is, the wheat, corn, and cotton, depending on this water, have no proven large-scale backup plan. The whole system is running on profoundly borrowed time.
And the physical consequences of pumping this hard are just devastating. Since the 1950s, the saturated thickness of the Ogallala has dropped by 30%. Over in the North China Plain, yanking water from deep fossil aquifers is causing the land to literally sink, a process called subsidence, by up to 10 centimeters a year near Beijing. In California's Central Valley, the ground has actually caved in by up to an unbelievable 9 meters over the past century. And here's the permanent tragedy of all this. Subsidence destroys the aquifer storage capacity forever. Once those deep sediment layers collapse under the weight of the earth, they can't re-expand. Even if we magically got the water back, there'd be nowhere to put it.
Okay, Section 4, the salt in our soil. Let's move to how this invisible threat actually builds up. You see, all irrigation water, even perfectly fresh water, has tiny amounts of dissolved salts and minerals from rocks. Step 1, we flood a field with this water. Step 2, the pure H2O evaporates or gets sweat out by the plants. Step 3, those dissolved salts, they don't evaporate. They're left right there in the dirt. Fast forward a few seasons, if the field isn't drained perfectly, these salts quietly build up, which leads to Step 4, osmotic stress. It essentially makes it physically impossible for plant roots to suck up water, even when the dirt around them is soaking wet. It's wild.
Now, farmers are smart, and they can adapt, up to a point. We've got salt-tolerant crops like barley, sugar beets, and cotton. They can take a lot more punishment than sensitive crops like strawberries or onions. But here's the catch. Even the toughest crops in the world can't survive forever in heavily salted soil. Eventually, the land simply dies. And actually, this isn't just some modern theoretical warning. Ancient records show that this exact process of soil salinization likely helped trigger the total collapse of the Sumerian civilization in Mesopotamia over 4,000 years ago.
Finally, we reach Section 5, the tragedy of the Aral Sea.
So the Aral Sea actually used to be the fourth largest lake on the entire planet, but in the 1960s, Soviet central planners decided to divert almost all the water from its two main rivers into a huge irrigation grid. Why? To literally turn a desert into farmland to maximize cotton production. And the crazy thing is, agronomically, it worked. Uzbekistan became a massive cotton exporter, but by starving the lake of its water, by the 1980s, the sea literally split into two distinct lakes. Fast forward to 2007, it had shrunk to just 10% of its original size, and by 2014, the eastern basin was completely gone, just dried out. They turned a vibrant sea into a brand new desert.
And this brilliantly illustrates just how massive the devastation really was. Before the diversion, you had a 68,000 square kilometer lake with fresh, low salinity water supporting a huge commercial fishery, tens of thousands of jobs. After the collapse, just 10% of the water is left. The salinity absolutely skyrocketed to over 100 grams per liter, which is more than 10 times saltier than the ocean. It killed every single fish. But it gets worse. That exposed, dried-up lakebed turned into a colossal source of toxic, pesticide-laced salt dust. Today, that dust blows across the region, causing some of the highest rates of respiratory disease, throat cancer, and infant mortality anywhere in the world.
As our source text so chillingly puts it, the Aral Sea is the most visually dramatic example of demand-driven resource exhaustion in the 20th century. You really have to understand, this was not an oops moment. The planners knew exactly what they were doing. They made a perfectly rational choice if your only goal is maximizing cotton. But they completely externalized the terrifying costs onto the lake, the local economy, and the lungs of the people living there.
So the crucial point is this. What does the word sustainable actually mean when we're heavily relying on fossil water that takes tens of thousands of years to replace? We've just seen how water literally has no substitute. We've seen how inefficient watering drains our future, how invisible salts poison the earth, and how large-scale farming diversions can literally wipe seas off the map in a single lifetime. As we try to figure out how to feed a rapidly growing population, we absolutely have to rethink everything we've looked at today. The clock is ticking, and the alarm is ringing right beneath our feet. Thanks so much for watching, and as always, keep learning.